All right, let's pull back the curtain on hydraulic fracturing. Um, we're going deep on quality control today. Fracking is all about cracking open those rock formations,
Yeah.
to get the oil and gas flowing. But there's a whole lot more to it than just brute force.
Oh, yeah.
There's this whole system of checks and balances in place, like this meticulous dance of QA/QC to make sure things go right.
Right.
We're talking making sure the well's ready, the materials are good, even the crew knows what they're doing. Everything's got to be top-notch.
It really is fascinating. The attention to detail that goes into this QA/QC. You see even a tiny little oversight up here on the surface
Yeah.
can mean huge consequences miles underground. We're talking potentially millions of dollars lost if things aren't done right.
Okay, so it's not just about checking off boxes on a list. You got to understand those domino effects.
Yeah.
I'm guessing it all starts with the pre-job planning.
Absolutely. It's like getting ready for a major surgery. Before any equipment comes on site, there's a massive checklist. Engineers check out the wellbore's integrity, they double-check the cementing, map out exactly where everything's going to go. They even create a footprint map of the whole shebang.
A footprint map. That sounds really detailed. Why is that so important?
Well, think about it. You're moving heavy machinery, sometimes in the middle of nowhere.
Yeah.
That footprint map helps ensure that trucks can get where they need to go, make sure they've taken weather into account, even where communication lines need to run.
Oh, wow.
It's all about safety and efficiency, which at the end of the day saves time and money.
Makes sense. So it's not just the well itself, it's the whole operation running smooth.
That's right.
Literally.
Yeah.
But what about the materials they're using? Like, is there quality control on the water they use for fracking?
Absolutely. Water quality is scrutinized like you wouldn't believe. It's like this, any impurities can throw off the entire fracking fluid recipe, like a bad ingredient ruining a cake.
Okay, now I'm intrigued. What kind of impurities are we talking about?
Well, things like iron can mess up the fluid's ability to gel, or bacteria, which can really do a number on the viscosity.
Oh.
It's so important, in fact, that they even recommend using glass containers for the water sample.
Glass containers. That can't just be for aesthetics.
No, not at all. It's to prevent any lingering bacteria from previous samples from contaminating the new one. We're talking like lab levels of precision here.
That's some serious attention to detail. What happens if they do find contaminated water?
That's when things get really expensive. Bad fracking fluid means a less effective treatment, and that means less oil and gas produced, which hits the bottom line, right?
Yeah.
We're talking potentially millions of dollars lost, all because of some bad water.
Wow. That really puts it into perspective. So the stakes are high, and every little thing matters. And I'm guessing the scrutiny doesn't stop at the water. What about the fracking fluid itself?
Oh, that fluid goes through rigorous testing, almost like it's auditioning for a starring role. They check the viscosity, the pH levels, even its compatibility with the oil and gas that's already in the formation.
So it has to be a top performer,
Yeah.
able to handle the pressure and get the job done. What if it fails those tests?
Back to the drawing board. The fluid needs to meet some very strict standards. For example, the viscosity can only vary by 10%. If it doesn't meet those standards, well, you end up with a less effective treatment.
Yeah.
And as we've discussed, that can get really costly.
So they're not playing around. This fluid's got to be the real deal. But I imagine it's not just about the initial quality. How do they maintain that quality during the actual fracking?
Oh, you're hitting on a crucial point there.
Yeah.
It's not just set it and forget it. During the treatment, they're constantly adding a gelling agent to the fluid in real time.
Wow.
This gelling on the fly requires constant vigilance to make sure the mix is right.
That sounds like walking a tightrope.
Yeah.
How do they make sure they're getting the gelling right in such a dynamic environment?
They've got a pretty clever system dual monitoring. They use a flow meter and a graduated tub to keep tabs on how much gelling agent is added.
Double the checks, double the peace of mind. I like it. But we've talked a lot about the fluid. What about the other ingredients in this fracking recipe? What about the acid they use to prep the well?
Ah, yes. Hydrochloric acid, or HCl. It plays a crucial role in cleaning up the wellbore before fracking. Gets rid of any leftover drilling mud or clay particles. But one of the biggest challenges here is keeping that iron contamination under control.
Iron contamination. Why is that such a big deal?
Well, too much iron, and things get messy down there.
Eh.
It reacts with the HCl and forms this thing called gelatinous ferric hydroxide precipitate,
Okay, that doesn't sound good.
which is as unpleasant as it sounds.
What does this goo do?
It can really clog up the formation and hinder production, like trying to drink a milkshake through a clogged straw. Not very effective.
Right.
But luckily, they've got some simple tests to check those iron levels in the acid and make sure everything's good.
So it's like a quick checkup to avoid a major headache later on.
Exactly.
Makes sense. But I got to ask, is there ever a temptation to cut corners with this stuff? Like maybe use a cheaper acid that isn't quite as good?
That's where the ethics of the industry really come in. While below-spec acid might save some money up front, the potential consequences are severe.
Yeah.
You're talking about potential formation damage, reduced well productivity, even environmental concerns.
So the risks outweigh the rewards.
Yeah.
Like trying to save a few bucks on car maintenance and ending up with a blown engine.
Exactly. And just like you want to protect your car, these operators are highly motivated to keep their wells producing for as long as possible.
Makes perfect sense. Now, what about proppant? That's the sand or ceramic material that keeps the fractures open, right? Seems like a pretty crucial part.
Proppant, absolutely essential. It's the backbone of the whole operation, holds those fractures open so the oil and gas can flow freely. And the quality control around proppant, every bit as strict as everything else we've talked about.
So what does that look like? What's the actual inspection process when those proppant transports roll up on site?
It's like a high-security delivery. You got weight tickets being checked, QC samples being taken, full-on inspections to make sure everything's as it should be.
Okay, so they're not just dumping a random pile of sand down the well.
Yeah.
What are they looking for in those inspections?
Well, they're checking for moisture, which can cause the proppant to clump up, and finds those tiny particles that can clog up the formation. They even do a test for cement contamination where they mix the proppant with water and check its pH. It's almost like a DIY science experiment,
Yeah.
but it's actually a pretty effective way to catch problems.
I love that. That's the little details, right? The things you wouldn't expect. It really shows the thought that goes into this whole process.
Yeah.
So once that proppant gets the green light, the real action begins, huh?
Yeah.
What's happening on location as they're getting ready to do the treatment?
Oh, it's a scene of controlled chaos. Lots of moving parts. Imagine this. Additive inventories being double-checked. Blenders getting inspected for any residue from previous jobs.
Wow.
Constant monitoring of flow rates and pressures.
Sounds like a well-choreographed dance. Everyone knows their steps.
You got it.
And I'm guessing safety is top of mind.
Oh, absolutely. Safety is always the top priority, especially when you're dealing with oil-based systems. You got extra precautions, grounding equipment, having fire suppression systems ready to go, and absolutely zero tolerance for cutting corners when it comes to pressure testing.
Right, because we're talking about some serious pressures here.
Absolutely. Any leak or any weakness could have really bad consequences.
I bet. And I'm assuming there are checks on the equipment itself, too, making sure those massive pumps are ready to rumble.
You bet. Every single piece of equipment gets a thorough inspection. They even check the treating iron ears. Those are the clamps that hold those high-pressure pipes together. If those ears are deformed, it's like a ticking time bomb. They could explode under pressure, sending metal fragments flying.
Yikes. Definitely don't want to mess with that.
Yeah.
But all this checking, it's not just about precaution, right? It actually helps them figure out how to do the treatment.
You got it. Before the main treatment, they run a bunch of diagnostic tests.
Okay.
It's like gathering clues to tailor their approach to that specific well.
No.
These tests, they've got names like ISIP, step rate test, and mini-frac. And they help the engineers fine-tune the plan based on how the formation responds.
So it's like they're feeling out the personality of the well before they get to work? What's this ISIP test you mentioned? I've heard that term before, but I'm not really sure what it means.
ISIP stands for instantaneous shut-in pressure.
Okay.
It's a measurement that tells them how much pressure is holding the fracture open after they stop pumping. Think of it like measuring the strength of the fracture, almost like taking its pulse.
Okay. Makes sense.
Yeah.
So they're doing all these tests, gathering intel, basically customizing the treatment for each well. That's amazing. But once that main treatment starts, what are they watching for? I imagine those pressure gauges are going crazy.
Oh, yeah. Those pressure readings tell a story, and the engineers, they need to be expert interpreters.
Yeah.
Those changes in pressure can mean a lot of things. Maybe there's a mechanical issue with the equipment, maybe the fluid's behaving differently downhole, or even how the rock formation itself is reacting to the treatment.
So it's like they're reading the vital signs of the well, looking for warning signs. How do they make sense of all those pressure changes?
One of the tools they use is called the Nolte-Smith plot. It's a graph of the pressure data that helps them understand what's happening down there.
Okay.
For example, if the pressure keeps going up, that might mean the fracture is growing how they expect it to. But a sudden spike could mean there's a problem, like a screen out where the proppant's blocking the flow.
So it's about recognizing patterns and knowing how to respond. That sounds incredibly complex. But they're not just watching the pressure, right? They're keeping an eye on the fluid itself, too.
Absolutely. They're constantly taking samples and running tests to make sure the fluid's still doing what it's supposed to, like checking a patient's vitals during surgery.
I see the parallels.
Yeah.
What kind of tests are they running on this fluid in the middle of the treatment?
Well, it depends on the type of fluid. Linear fluids, they'll check things like the viscosity and the pH, cross-linked fluids. They're looking at the cross-linking time and the temperature. And with energized fluid, it's all about foam stability and how well it's performing down there.
Yeah, there's really no room for error here. Every step of the way, they're checking and double-checking everything. It's like a high-stakes operation. Constant vigilance is key.
Mhm.
But what happens when the treatment's done? Is that when everyone can finally relax?
Not quite. There's still a crucial piece of the puzzle. Post-frac analysis.
That makes sense. I'm sure there's a lot of data to process and lessons to learn from each treatment. What exactly happens during that post-frac phase?
First, they take another ISIP measurement, which tells them a lot about how effective the fracture is.
Right.
Then, it's all about collecting and analyzing the data. Digital files, hard copies, fluid samples, everything is carefully documented. They also sit down with the service company to talk about what went well, what could be improved, and make sure they're always learning and refining their approach.
So it's a constant cycle of improvement, always trying to get better.
Absolutely.
But with all this focus on data and technical stuff, it's easy to lose sight of the big picture.
That's where the human element comes back in. Despite all the complexity, the goal of this whole process is pretty simple: to get the most out of that well, to produce as much oil and gas as possible safely and efficiently.
Right, because at the end of the day, it's about producing energy to meet the world's needs. But before we wrap up part one of our deep dive, are there any final checks or maybe questions engineers should be asking themselves after a treatment is done?
There are 3 key questions every engineer should be asking,
Okay.
and they all come back to that ISIC measurement.
Okay, I'm all ears. Hit me with those questions.
First and foremost, did everyone get home safe? Because safety is always the most important thing. Secondly, did the job go as planned? Meaning, did they get all the planned materials in place? And finally, the million-dollar question: what was the difference in ISIP from the start to the end of the job?
Okay, that last one has me intrigued. Why is that ISIP change so important? What does it tell us about how successful the treatment was? I guess we'll have to wait for part 2 to find out.
Yeah, that ISIP question, that's where the money is. It tells us how well we've created those pathways for the oil and gas to flow.
All right, you got me hooked. Lay it on me.
Ah.
How does this ISIP relate to a well's profitability?
Yeah. Well, remember, ISIP stands for instantaneous shut-in pressure. It's the pressure holding the fracture open after we stop pumping. If that final ISIP is higher than what we started with, that means we have a wider, more stable fracture. And a wider fracture equals more space for those valuable hydrocarbons to flow.
Ah, so it's like widening a doorway. The bigger the door, the easier it is to get through.
Exactly. A narrow fracture chokes off the flow of oil and gas, kind of like a crowded doorway. And that limits how much the well can produce.
So a bigger ISIP increase, generally, that means a more productive well.
That's the gist. It suggests a more effective treatment, a better chance of good production. But it's not the whole picture, of course. The type of rock, the reservoir pressure, even the price of oil and gas, all of that factors in.
Right, so it's a complicated equation, but I'm starting to see how this quality control helps things go right.
Speaking of right, don't forget about the sheer amount of calculation that goes into fracking. Lots of math going on behind the scenes to make sure they're using the right volumes, the right pressures, the right concentrations.
Oh boy, here comes the math. Is it really that complicated?
It can be, but it's all about optimization.
Okay.
For example, they got to calculate the horsepower needed to pump the fluid at a certain rate and pressure.
Yeah.
And there are formulas for converting clean fluid volume to slurry volume once you add the proppant.
My head's already spinning.
It's all right.
Could you give me, like, a real-world example?
Sure. Let's say we have a job with a max pressure of 10,000 psi and a max pump rate of 30 barrels a minute. To get the horsepower, we multiply those two numbers and divide by a constant. So in this case, we'd need over 7,300 horsepower.
Wow. That's a ton of power. No wonder those pumps are so huge.
They are.
What about the slurry volume calculation?
Actually, that one's pretty straightforward. We take the clean fluid volume, let's say a gallon. And we add the volume of proppant divided by its density. So if we're adding 5 pounds per gallon of bauxite proppant, our slurry volume goes up to 1.1 thousand gallons.
So the proppant really bumps up the overall volume.
Yeah.
And I bet that affects the pump rate too.
Absolutely. We multiply the clean pump rate by 1 plus the proppant volume divided by its density. So in our example, a clean rate of 20 barrels a minute becomes almost 23.5 with the proppant.
All right, starting to get the hang of this math now.
Yeah.
But why is it so important to get these calculations right?
Precision is everything. We need to deliver just the right amount of proppant to the formation. Too little, the fracture might close up. Too much, you risk a screen out. That's where the proppant blocks the flow.
So it's all about finding that sweet spot. And it sounds like all these calculations, along with all the quality control, that's what helps them do it.
It does.
But who's actually calling the shots out on location? Who's making sure everything runs smoothly?
Well, the service company, they bring the equipment and the expertise, right?
Yeah.
But it's the production company, the folks who own the well, who are ultimately in charge. And the guy leading the charge for them is usually the well site engineer.
So they're kind of like the conductor of the whole fracking orchestra, making sure everyone's in tune.
Perfect analogy. They oversee everything, from pre-job planning to post-frac analysis. They're talking with the service company crew, making sure things are on track, troubleshooting problems.
Hey, what makes a good well site engineer? Seems like a tough gig.
First and foremost, a solid understanding of fracking. They got to read the data, understand those pressure changes, and make good decisions based on what they see.
So it's not just checking boxes, it's thinking on your feet, problem solving.
You got it. But technical skills aren't enough. They need to be great communicators, good leaders, able to manage the crew, coordinate with everyone, and keep everyone safe. It's a high-pressure environment, literally and figuratively, so staying calm under pressure is a must.
Sounds challenging, but important. Now, we've covered the pre-job checks, the real-time monitoring, and the post-frac analysis. Are we missing anything? Any key stages we haven't talked about yet?
There is one crucial stage we haven't mentioned. Flushing.
Oh yeah, flushing.
That's the final act of the treatment. You got to clear out any leftover proppant and fluid from the wellbore to make way for the oil and gas.
Flushing. Seems pretty straightforward. What's the big deal?
It's more complicated than it sounds. We got to flush it good without overdoing it, which could damage the fracture. And we got to be careful not to have proppant flow back, which could plug up the well.
So it's like a balancing act. How do they get this flushing just right?
One of the key tools is the densitometer. It measures the density of the fluid coming out.
Okay.
As the proppant concentration drops, that tells us we're nearing the end of the treatment. That's when we start flushing.
So the densitometer is like the signal to start wrapping things up. What happens next?
We try to flush to a point just above the perforations. Those are the holes in the casing that let the fluid into the formation. This makes sure we get all the leftover proppant near the wellbore.
Got it. So the flushing is like a final cleanup, making sure everything's tidy for the oil and gas to flow. But what happens to all that fluid and proppant they pump down there? Doesn't just disappear, does it?
You're right. It's got to go somewhere. That's where the flowback process comes in. It's where we manage the return of fluids and proppant from the well, making room for the oil and gas.
Flowback. Sounds kind of messy.
It can be, yeah. But it's a critical part of the operation. And like everything else, flowback needs to be closely watched and carefully managed, both for safety and to get the best production.
So how do they keep things from going haywire?
We start slow and gradually increase the flow rate, kind of easing the well back into production.
Okay.
We use a special manifold with chokes. Those are valves that restrict the flow, helps us control the pressure and the rate.
So you're easing the well back in, not just opening the floodgates all at once.
Exactly. And we're watching carefully, looking for signs of trouble, like proppant flowback, anything that needs our attention.
What are some of those like red flags they're looking for?
Too much proppant coming back up, that's not good. Could mean the proppant pack isn't stable. Or maybe we damaged the fracture. We also keep an eye on what's in those flowback fluids. Any changes might mean there's a problem downhole.
So they're analyzing everything, like detectives looking for clues.
That's a great way to put it. We're using that data to make smart decisions, protecting the well and maximizing production. And speaking of data, the flowback itself can tell us a lot about how well the treatment worked.
Oh, really? It's not just about getting rid of the waste fluid. What kind of information can they get from it?
Well, for instance, we can look at how much of the original water we get back, the load water.
Okay.
This helps us figure out how much was lost to the formation, how big the fracture is, and how successful the treatment was overall.
It's amazing what they can learn from these fluids. What else do they monitor during flowback?
We keep a close eye on the pressure and the rate of the flowback, looking for changes that tell us how the well is cleaning up and how easily the oil and gas are coming out.
Right, because a clean, productive well is what it's all about. But even after flowback's done, the work isn't over, is it?
Nope. Still one more crucial step: the post-job evaluation. That's where we step back, look at all the data, and see what we can learn to improve future treatments.
So it's a continuous process, always learning, always getting better.
That's the goal.
I imagine this involves both the production company and the service company working together.
Oh, yeah, absolutely. It's a team effort. The service company, with their specialized knowledge, gives feedback on how the treatment went. And the production company, knowing their well and the reservoir, adds valuable context to the overall performance.
It really is a partnership, isn't it? But let's be honest, this is oil and gas, so the bottom line is a big factor.
Right.
How does all this quality control affect the money side of fracking?
Hydraulic fracturing is a huge investment. The equipment, the people, the materials, it all adds up. Anything that helps improve efficiency, reduces risks, and maximizes production that has a big impact on profitability.
So wasted time, wasted materials, redoing things, all that eats into profits.
Exactly. And that's where quality control really pays off. By doing it right the first time, you minimize those costly mistakes and delays.
It's like the old saying, an ounce of prevention is worth a pound of cure.
And don't forget about that ISOP increase. Remember that.
Yeah.
That's a sign of how well those fractures are propped open, which means more production and more money.
Right, those nice wide fractures mean oil and gas can flow freely. But it's not just about maximizing production. It's about doing it safely and responsibly, right?
Absolutely. That's another huge benefit of good quality control. By sticking to high standards, being thorough with inspections, and putting safety first, we can minimize the risks that come with this complex operation.
So it protects the investment and the environment and the people involved.
That's right.
But even with all these precautions, fracking is still controversial. What are some of the things people are concerned about?
One big concern is groundwater contamination. Folks worry that those fracking fluids, with all those chemicals, might leak into aquifers and pollute drinking water.
That's a serious worry.
Yeah.
What does the industry say about that?
Well, they maintain that fracking is safe and well-regulated, with lots of protections in place to prevent groundwater contamination.
Okay.
Those fractures are created way below freshwater aquifers, and they use steel and cement casings to seal off the wellbore and prevent leaks.
So it's about distance and barriers to keep those fluids away from the groundwater?
Exactly. Plus, the industry is always researching new, more environmentally friendly fluids
Yeah.
to reduce that risk even further.
That's great to hear. But it sounds like groundwater contamination isn't the only concern.
You're right. Another one is what they call induced seismicity. Basically, earthquakes that might be triggered by fluid injection.
So the fracking itself could cause earthquakes.
It's a complex issue. The science is still developing.
Right.
But there's some evidence that injecting large volumes of fluid could increase pressure on fault lines and potentially cause tremors.
That is a scary thought. What's being done about that?
They're trying to understand the link between fracking and these earthquakes better. They're developing better monitoring techniques, and they're coming up with strategies to reduce the risks.
So it's about understanding the data, analyzing the risks, and changing how they do things accordingly.
That's it. Sometimes that means using less fluid or pumping at lower pressures, or even picking different drilling locations to avoid those sensitive areas.
Makes sense. It's all about finding that balance.
Absolutely.
Weighing the need for energy with the need to protect the environment and keep people safe.
Exactly. It's important to remember that fracking is constantly evolving. They're always doing research to make it safer and more efficient.
So it's not just a one-and-done thing. It's a field that's always changing.
That's right.
Well, it seems like our time for part 2 is just about up. But before we go, what about the future of fracking? What are some of the exciting new developments that are shaping the industry and its quality control? I guess we'll have to wait for part 3 to find out. Okay, we're back for the final part of our deep dive into fracking quality control. And we left off talking about what's next for the industry. What does the future hold?
The future of fracking. It's a pretty exciting time. One of the coolest things happening is how they're using data analytics and AI.
Data analytics and AI. That sounds incredibly high-tech. Are we talking about algorithms taking over oil fields? Like, are robots going to be running the show?
Well, not robots exactly,
Yeah.
but definitely a lot more data. It's like giving engineers these super powerful tools, to analyze all this information, spot patterns, and make better decisions.
So instead of just going with their gut, They're getting real-time insights from the data.
Exactly. These AI systems can do some pretty wild stuff. They can
Mhm.
predict the shape of the fractures, fine-tune the fluid mixes, even automate parts of the quality control.
Wow, it sounds like science fiction. But what does that actually mean in the real world? What's the real impact?
Well, it's not just about making things easier. It's about getting things right. Reducing risks and ultimately making fracking as efficient as possible.
That makes sense. Small improvements can have a huge impact on costs and production. Are there any other innovations out there?
Another really cool area is how they're developing these greener fracking fluids. Remember, we talked about those concerns with groundwater. Finding cleaner alternatives is a big deal.
Right. Those chemical-heavy fluids can be a real problem. What are they doing to clean them up?
They're looking at all sorts of options, like biodegradable polymers
Yeah.
and just using fewer chemicals overall. CO2-based fluids are becoming popular too. They have a much smaller impact on the environment.
It's encouraging to see them working on getting the job done while minimizing the downsides.
Yeah, it's part of this larger trend in the oil and gas world, moving towards sustainability. It's not just about getting the resources out of the ground anymore. It's about doing it right.
That's great to hear. We've talked a lot about the environmental side of things, but what about how fracking impacts communities?
That's an important point. Fracking has created a lot of jobs and boosted the economy in a lot of areas.
Yeah.
But we need to be really careful about how it impacts the people who live nearby. Things like noise, traffic, how it affects roads and other infrastructure, all that needs to be carefully considered.
So it's about finding that sweet spot, balancing energy production with taking care of the people who live there.
Exactly. Open communication is key. Being transparent and being willing to listen to concerns. That's how we can build trust and find solutions that work for everyone. And the industry is starting to get that.
Well, as we wrap up our deep dive into fracking quality control, it's obvious that this is a really powerful technology, and it comes with some big responsibilities. What's the one thing you really want our listeners to remember?
I think the main takeaway is that fracking, like anything powerful, has to be managed carefully. It's all about understanding the risks, pushing for innovation, and constantly working to make it safer, more efficient, and better for the environment.
That's a great point. We rely on oil and gas for energy, so it's vital that we keep having these open and honest conversations about how to do it right.
Absolutely. And hopefully this deep dive has given folks the information they need to be a part of those conversations.
I think it has. We've gone from the very beginning all the way through to the end of a fracking job and learned a lot along the way. It's been a real eye-opener for me, and I hope for our listeners too. And as always, we encourage everyone to keep learning, keep asking those tough questions, and stay curious. That's what the deep dive is all about.